Okay, so hello everybody. This is Luboš Pirkl from CFD Support. I am here in our Prague office with my colleague Radek Máca. Hello Radek.
Hello Luboš.
How are you today?
Yeah, I'm fine. The technique is working, so everything is fine. And how are you?
Yeah, I'm also fine. So it seems we are ready, and also together with us on the line there is Oliver Felde from CFturbo in Dresden. Hello Oliver.
Hello, Luboš to Prague.
Yeah, the same question to you. Is everything okay? Are you ready for the webinar?
Yes, I'm ready. Everything is set up, and I'm looking forward to having the webinar with you.
Okay, it's perfect. So it seems we all are ready. So let's go ahead. So hello again, everybody. Welcome to the webinar on turbo machinery design and analysis. In today's webinar, we would like to show you an easy way how to design a centrifugal fan from scratch in CFturbo, and then how to simulate and evaluate it in turbo machinery CFD. The webinar is being recorded, and its recording will be made available on our YouTube channel. And the rest is, I believe, everything is okay. In case of any technical problems, feel free to contact us in the future, and we will gladly answer all your questions and comments. So please let me start with who we are. So I'm gonna introduce us a little bit. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support. I am here in our Prague office with my colleague Radek Máca. Radek is our head engineer and senior developer here at CFD Support. And finally, in Dresden, there is Oliver Felde. Oliver is senior manager CAE at CFturbo. He is responsible for consultancy and software development, especially for the implementation of turbo machine design theory and related algorithms in CFturbo software. Okay, about the program of today's webinar. So the webinar is going to take about one hour, depending on the number of your questions and comments. There will be 4 parts in this webinar. In the first part, which is basically this general introduction, there will be a second part, let's call it the design part or CFturbo part. There will be a live example where Oliver is going to introduce CFturbo a little bit, and then he will show a live example of centrifugal fan, how it's going to be designed in CFturbo, and with final export of the designed model to turbo machinery CFD. In the next part, let's call it the simulation part or turbo machinery CFD part, there will be other live example where Radek is going to show you the turbo machinery CFD simulation and evaluation of that centrifugal fan, which was exported by Oliver from CFturbo in the previous section. Yeah, and in the last part of today's webinar, there will be a Q&A session, which will be dedicated to your questions and our answers. Feel free to put your questions to the special window, or you can also send us an email to info@cfdsupport.com. We will answer all your questions later in this webinar. Feel free to put your questions. It's your time. This is quite important part of this webinar. You can learn quite a lot. You can ask. It's your time. So just take your chance. Okay, which brings me to the CFturbo part of this webinar. So I'm gonna hand over the presentation to Oliver. So Oliver, will you tell us about CFturbo?
Yes, I will. Okay, CFturbo is a company based in Germany. We have 2 locations in Germany. One is Dresden and the other one is Munich. Our main product is the design software CFturbo. It's a modern and powerful user-friendly software tool for the design, for the conceptual design of turbo machines and its components. And it's based on latest design theory. can you go ahead? Okay,
Okay.
thanks. Thanks, Lubos. Right now we have 200 active clients globally, and we see an ongoing growing process. CFturbo has different modules implemented to design pumps, ventilators, which are fans and blowers, compressors, turbines, plus stators and diffusers, and of course volutes if there is a radial or centrifugal turbo machine to be designed. The industries we serve are aerospace, automotive, consumer products, energy, oil and gas, marine, and also just mechanical and process engineering, plus the semiconductor industry.
Okay, so I think we can make you an organizer, and you can share your screen now and show the real life example in CFturbo.
Yes. Okay, thank you, Lubos. Okay, today I'm going to design quite a big centrifugal fan. As always, in case one wants to design something from scratch, it is necessary to first choose the machine to be designed, and secondly, set up or define the operating point the machine should run it most of the time, because what we are doing is a best efficiency point design. I want to design a machine that has got a flow rate of 38,000 cubic meter per hour at a pressure difference of 0.64 bar, and it should run on roughly through 3,000 RPMs. The fluid to be conveyed should be air, but this time it should be air with a higher temperature, which has a certain impact on the density. Here, inlet conditions consisting of total pressure can be defined. It's not necessary for the design itself, but it's necessary for the setup of the following simulation in any simulation package. Okay, once that is done, CFturbo asked me which kind of component I want to design first, and because the impeller is the central or the most important component of the stage, I'm going to start with the impeller. The design process for the impeller always consists of a set of different design steps. The first one is the definition of the main dimensions, and the main dimensions just consist of inlet diameter at hub and shroud, impeller's diameter, and the outlet width. Because we call the software a conceptual design, the user is always guided through the design process and has got the chance to either use CFturbo proposals or do its own dimensioning. CFturbo proposals are based on fundamental balance equations like Euler equations or continuity equations, plus empirical data that are implemented and that can be seen and changed also by the customer. So here, for instance, we have a diameter ratio given with respect to the specific speed, and the source is given. And in accordance to the design point, you always get a proposal by CFturbo for instance, the specific speed, and that would be here something like 0.325 or so. Anyway, that's given for all empirical data, and the data, as I said, can be overwritten by the customer and can be stored on his local machine so that the knowledge will stay in-house. Very important is to have an idea about the efficiencies one can get with this kind of machines. Again, they are based on empirical data and can be taken from what we call the approximation functions. And once those data are set either by default or by user input, one can have CFturbo to calculate on that basis, plus the balance equations, these four main dimensions. And I'm going to do that by just clicking on calculate, and I get these proposals. And what I want to show here is what would happen if I would change a parameter. And to this end, I'm check this automatic checkbox, which means that after any parameter change, the main dimensions will be calculated newly. So for instance, if I change the diameter coefficient, of course, then the impeller's diameter must go through a change. Okay, once I'm happy with the things, I deactivate that automatic feature because I want to freeze in those values. And also at any time I can just get rid of the decimal places, which I want to do now. And yeah, and maybe change the data a bit. Okay, the next design step is the meridional contour design, which is done in that second meridional contour design step. Because that's a simple centrifugal fan, the harp and shroud contours are consisting of lines and at the shroud of one arc, but at any time one can just right click on it and change the shape to, for instance, Bezier. And once that is done, of course, one has a lot more freedom to design the contour here. Also, by grabbing the control points, I can change the actual extent. So maybe make that a bit bigger, or grabbing that arc control point here, and so on. What I can also do is right-click on any of the control point, go into the context menus and change the values there manually. And by doing so, I get exactly the inlet conditions I want to have. Also, what I can do is I can change the locations as well as the shape of the leading edge. And for instance, here I want to have it still straight, but I don't want to have it radial, and that's why I'm changing the position of it like that. And now I'm happy with that, but I want to show you that analyzing feature which is implemented. It's a potential flow solution for the meridional velocities in that meridional contour. And from that you can see, for instance, that where you have small radii, you would get higher acceleration, and at a hub it would be smaller, and so on. Okay, once I have pressed OK, I can see that something has happened in the 3D model, because now we have a real 3D shape. But of course, nothing has happened so far for the design of the blades yet. To this end, I'm going to open the third design step, which we call the blade property design step. Here, one can or has to define the number of blades, the general shape of the blades, because that's the centrifugal fan, and they are very often quite easily manufactured. I'm going for the circular 2D shape. Also, one has to have an idea about the thickness of the blades, which I'm going to change to 6 millimeters here. And because there's always a certain difference between the direction given by the blades and the actual relative flow. There is either a deviation angle to be defined, or the user should make use of the built-in deviation or slip models that are given here. Okay, I'm still sticking to 10 degrees on the hub. This time it's just at the hub defined, because it's the circular shape means that one can only have one kind of master span, and all the others will follow the geometry of that master span in accordance to that blade shape. The second tab holds the blade angles at leading and trailing edge. Again, they are calculated on the basis of the Euler equation plus the deviation angle plus a incidence which might be there and might be defined by the user in that incidence group. Okay, once that is ready, there won't be any change in the 3D model, because the only thing that has been defined now are the inlet and outlet angles. The shape itself will be defined in the next design step, which we call the meanline design step. As you can see here, there is just an information panel where no interaction is possible. The reason for that is that circular shaped blades are totally defined with the inlet and outlet angles plus the inlet and outlet diameters, and that's why nothing can be done here. But one can at least see the 3D preview and can make use again of built-in potential flow solutions to check the geometry defined so far. Again, if I press OK and go back to the 3D model, what I can see is an impeller with blades that have a thickness of 0. And also one can see where is the location of the smallest cross-section or blade-to-blade section between two adjacent blades. Of course, it's not ready yet, so the next design step is to put some thickness on that mean surface that has been just defined, and to this end the blade profile dialog can be used. Here one can use the initial thickness of 6 millimeter and define a certain distribution of the thickness over along the blade at hub and shroud. One can have it linearly distributed, or one can have Bézier curves again to distribute the thickness. One even can, by right-click on it, load thickness distributions from a built-in profile manager, or one can also load polylines holding thickness with respect to the dimensionless length of the scale of the blades. Okay, but I want to stick to the simple approach with just 2 control points and a linear distribution. And once I press OK here, I can see that now there is a certain thickness applied on the mean surface, and the very last thing to finish this design of the impeller is to shape leading and trailing edge, because you can see here at the trailing edge that the blade is not within the meridional contour, and also the leading edge is very sharp, and that's why the last design steps gives the opportunity to shape that leading edge, for instance, with the help of an ellipsis. And here you can give the half axis ratio of the radii, and the default is 3. If I type in 1, you see that this will be circular, but 3 is I think a good will lead to a good elliptic shape. On the other hand, at the trailing edge, one wants to have it trimmed with the outlet, and that's why this simple mode is applied here, and you can see that here in that frontal view that now the trailing edge is not looking out of the meridional contour anymore. Okay, now if I go to the 3D model, it's done. The only thing I want to do before I go further on to add a small outlet extension, which will give some of the simulation package more freedom in the simulation process. And to this end, there is a virtual design step called CFD setup, where one can add this little gap at the trailing edge, and it can have a certain length. So, for instance, 6 mm in this case. And if I add this, I'm done with the impeller, and I want to save that and give them, of course, the name test, which is already there, but I'm going to overwrite it. Okay. The next step is to add a volute at the outlet of the impeller. And one can do that by clicking on the interface and telling him that there should be a volute defined there. Again, one starts with the inlet setup consisting of inlet diameter and inlet width. And defaults are given by CFturbo, and they can be overwritten according to the customer's wishes. So I want, for instance, have it a bit wider than proposed by CFturbo, and maybe not at this location. And that's why I'm going to increase that inlet width here quite a lot. Next step is to define the general cross-section or the general cross-section shape. And it is done here, and because it's such a simple centrifugal fan, I will stick to the default setting of CFturbo, which is the rectangular shape. But as you can see here, if I click on that combo box, there are a lot of different shapes, and there are also Bezier-like shapes or line segment shapes where you can roughly define any geometric shape you want to have. Also, there is the possibility to add sections, which means with respect to the wrap angle, one can change the shape and have very elaborated shapes of the spiral. But again, it should be simple. That's why I'm choosing rectangular. Press OK. Of course, in the 3D model, nothing has changed yet because the design of the spiral will be done in the third design step. Here, the shape is scaled at any wrap angle location in accordance either to some design rules or in just what we call geometry-based in accordance to a certain either outer radius distribution or area distribution. So for the initial design, it's probably wise to choose a design rule, and one of them is Fleiderer's rule. He made that swirl approach where one can choose between different swirl exponents. And if I leave everything to default, I get something like that, where my last radius is something like 655 millimeters. And if I press OK and go to the 3D model, then I see now the volute. Still missing is an outlet diffuser plus a proper cutwater. The outlet diffuser is defined in the next design step, where one can tell him how long should be that diffuser and what should be the end cross section. The end cross section can be circular again with a certain diameter, or rectangular, which is the one that I want to go for. And because the inlet width into the spiral was 300 millimeter, I'm going to type in the width of 300 millimeter for the diffuser here as well, because then one can just cut metal sheets and weld them together, and one can, in a very simple manufacturing process, make up that ventilator stage. Okay, and now what you see is the volute with a very sharp cutwater, and that's why the last step is to add a cutwater at a certain position here. So for instance, I can change that to 30 degree, and again, if I press OK, you see now it's almost done. I should save that again. Because we have a little gap between the impeller and the volute, for the simulation process, one has to close that gap, which is done in the volute CFD setup. So checking the rotor stator interface connection will yield to that closing, but one can also extend the outlet diffuser by another virtual component in order to support the simulation process that might follow the design. Okay, so the very last step is then at the end go back to the impeller and make there what we call a model finishing with solid trimming. Here we use the built-in cut kernel in order to extend all surfaces and get very nice intersection of it, and by doing so producing very nice watertight solids that can be used in the 3D export steps, as well as for simulations and so on. Okay, once I have done that, the last step before I give the ball to Radek is to show the export panel, because there are a lot of oh, that was missing. There are a lot of that doesn't matter. Interfaces implemented. One is the turbo machinery CFD interface. Once that is chosen, I have to choose which component has to be incorporated in the design in the export process, and also what are the triangulation parameters for the STL triangulation. And once that is done, I can start the export process. All the necessary data are written, especially the TCFD file, which holds all the data necessary to set up the simulation process in TCFD. Okay, and saying that, I'm finished, and I would ask to take over and carry on.
Okay, thank you, Oliver, for the turbo machinery design part. It was very impressive as usual. It took, yeah, I'm always impressed because it took you like 20 minutes to design a centrifugal fan from scratch. And yeah, let's move in the presentation. So I'm gonna take back um, the presentation, and yeah, it's time to switch to the turbo machinery CFD part of this webinar. And before I do that, I would like to ask the audience I would like to encourage you to put your questions. So feel free to put your questions because it's still, yeah, it's your time, and it's also an interesting feedback for us, and you can learn what you are interested in. So yeah, so feel free to put your questions. I'm gonna continue. So I'm gonna give a brief description of what turbo machinery CFD is. So turbo machinery CFD is a unique software developed by Czech company CFD Support. It's smart and easy to use CFD software. Turbo machinery CFD was designed for CFD simulations of all rotating machinery such as fans, pumps, compressors, turbines, turbochargers, hydro turbines, all of them, both radial and axial machines, both compressible and incompressible fluid flows. Turbo machinery CFD is based on OpenFOAM, and we believe turbo machinery CFD is unique, at least for reasons. So I will quickly go over them. So we believe turbo machinery CFD is unique because it has no licensing policy, which means our clients can keep turbo machinery CFD forever, and they can use it for unlimited number of users, jobs, or cores. We have different business model than standard CFD codes. With turbo machinery CFD, what is paid for is the first delivery and later technical support and software maintenance. This gives the investment in turbo machinery CFD a permanent value, and also this means our clients can scale their CFD simulations in a really big way. Number two would be turbo machinery CFD is fully automated, which means all the workflow from the initial data to the final engineering results, it can be run by a single command or a single click in graphical interface. And all the process is being done automatically. And for this reason, turbo machinery CFD is also extremely effective. Yep. Number three would be we deliver an extensive technical support with turbo machinery CFD. We keep custom approach to every customer, to every issue. We never leave behind any of our clients. We are very flexible in it. Turbo machinery CFD technical support is unlimited. We support our clients even in matters out of turbo machinery field, for example, numerical mathematics, physics, CFD, IT, or even software engineering. And the last one would be the real tutorials are included in turbo machinery CFD, so the TCFD user has no doubts about the best practice settings. There are included the real machines that are already preset. So user can basically take one of those tutorials, replace the geometry and the physical data and settings, and run the simulation. The rest of the workflow is automated, so the requirements, also the requirements on the user's skill, on CFD skills are quite low. There are many other benefits of using turbo machinery CFD. I'm not going to go for all of them. I finish here with my last point, that at CFD Support, we believe the future of CFD is the automation. In CFD, everything can be automated. The automation is extremely effective. It's even more effective than we expected in the first place. So nowadays at CFD Support, we think only in automated sense. So this brings a huge value to our users. I think it's time to switch to Radek's part, which is a live example of turbo machinery CFD simulation of that fan, exactly that fan that Oliver designed in CFturbo. So Radek, are you ready for your part?
Yeah, yes, I am. So please, can you give me
of course.
The presentation?
Okay, I think it's
okay. So show
now,
my
so
screen.
you can go ahead.
I believe you can see my screen.
Yes, we can. So you can.
Okay, perfect. So good afternoon. I will start directly because Luboj has already said all important information. So I will jump directly into the practice. So I have about 15 minutes to show you how easy it is to use Turbo Machinery CFD. I prefer to introduce you basic principles rather than to show you the very details in CFD setup. So I will really show you the basics, and we are going to use the export from CFturbo. So this makes a workflow even simpler. So as you will see in a few moments, with CFturbo and TCFD, we are now able to run a CFD simulation and get significant results just by few mouse clicks. So let's start. So we simply start from data which Oliver has just generated. So basically, at the beginning, you need just to have the STL files, which define your geometry, and the configuration file, which is automatically generated from CFturbo, and basically it defines all necessary parameters which allows us to run directly the simulation without any modification. So it basically sets the fluid properties, simulation properties, it defines the geometry, and so on. So to start working, we need just to click on the configuration file, or we can, if we started from scratch, we can just click on this icon at the desktop. So I will click on this Radial Fun configuration file, and the new ParaView session will appear directly. So actually I am using a brand new version of our Turbo Machinery CFD, which is going to be released next week. So to start using it, I just click on Apply button, and in few seconds the input geometry will appear. So this is the geometry which has Oliver generated. This is a standard layout. Here you can see the geometry. Here you will see the lock screen or lock window. So it shows the actual processes which is running. Here is the pipeline browser, so we can add other filters to work with TCFD. And important part is these menus, which contain the setup of all necessary parameters. So everything is preset. So I will go through this just very quickly. So here in general, you can load, save, or overwrite the configuration file. You should set the machine type which you would like to simulate. This defines coordinate system of the rotation. In this geometry, there are some parameters, for example, to scale the geometry, physics setup, so the setup of the fluid. Of course, you can set the turbulence model. Here in the speed lines menu, here you can define more points, which I actually, this part I actually modified, because from CFturbo you get 1 point to simulate, which should correspond to the best efficiency point. But for validation or for generation and efficiency maps, you can add more points to be simulated, or even you can add more speed lines to be simulated. So speed lines with different rotation speed. For each point, you should set the inlet boundary condition. For example, here we set the total pressure at the inlet, which corresponds to the ambient pressure and inlet temperature in kelvins. And other parameters, the same holds for the outlet. So here we use the special boundary condition outlet one, which is really suitable for generation of efficiency map. So it's a special boundary condition developed here in CFD support. Next menu is the simulation. Important menu here. Basically, the most important parameter is processors. So you can run the simulation at using any number of processor, usually the number which your hardware provides. So there is no limitation, there is no licensing policy, so you can use very high number of processors. Other advanced parameters, how to set some numerical parameters like relaxation and so on. Here are the initial conditions for the simulation. An important part is the components part. So basically here you define the computational mesh. So you have two options. Here we have defined the geometry using the STL files, or you can also import the external OpenFOAM mesh. So basically you can import the meshes from other softwares, which can be easily converted to OpenFOAM and use it here. For each component, so here we have two components, the red one and white one, impeller and the volute, and each part, for each part, we define the boundaries. So just by align the type of the boundary, set the refinement level, which is also set in default mode, but you can modify it. You can add layers, and for inlets and outlets, and usually for the interfaces between the components, you should add the communication between them. So if you add the number which is higher than 0, then the mixing plane approach is used, and if you set to the 0, then the arbitrary mesh interface is used. Okay, and here are other parameters to set. If you define the geometry from STL, so you should define the finest of the mesh. Again, it is set in default, but you can modify it. For example, important parameter is the background mesh size, which is the largest cell in the computational mesh, and more parameters to be set. Here is the topology graph, which is really nice during the setup part. So if you really setting, or if you setting your geometry from scratch, it is really nice because you see the actual topology, which part is connected to which part is rotating, and so on. So there are other parameters for the meshing. The meshing tool is actually the snappy hex mesh, and the last two menus. First, post-processing. So this is a new feature. So here you can define which parts will be used to evaluate efficiencies, pressure drops, and so on. So the default is inlet to the geometry and outlet from the geometry. Blade-to-blade views. You can define the blade-to-blade views, which will be automatically generated. So basically, what you should define, which component to evaluate. So default is the rotating component, and basically here you can set which field you would like to visualize and at which radial height between the hub and shroud. So I will, for example, add pressure, static pressure, or for example, relative velocity with LIC, which is the streamline filter, and so on. Of course, you can add more heights and more fields to evaluate. Meridional average, again, you can add the meridional average filter, and again, you get automatically nice visualization at the end of the computation. You can set, for example, total pressure to evaluate that, and other fields. And really nice feature is to add some old graph to compare with the new results. So you can add some old, for example, old data. I have here some old graph, and I can add, because I know that these columns defines efficiency and mass flow rates, and flow rate versus efficiency. So I would like to add all data to this graph. Okay, and the last one is the scripting, so you can add your own user-defined functions to set something which is not available implicitly in these menus. So whenever you are satisfied with the setup, you should approve it, or you should click on this apply button. So now the setup process is done, and afterwards we will apply this TCFD manager, using which we can manage all steps of the simulation. So at the beginning, we can define the name of the directory in which everything will be stored. So again, I need to click on apply button to approve my changes. Then first step is to write the case. So now the TCFD processor is writing all necessary files, directories, and other stuff to run the simulation properly. So here in the log file, you can see what is happening right now. And the first step, so you have two options. You can run all by one click, or you can do everything step by step. You can first mesh the geometry, then run the calculation, and then generate the report. So first I will click, for example, to mesh all. So now the meshing process is running. Now it's creating the mesh. So if I jump a little bit, which is here, yes, so now we are at the step where the mesh is generated successfully. You can visualize it by clicking at this show button, and here we can make the mesh visible by clicking on this eye and invisible components. And now we can check the mesh, for example. When we are satisfied, we can run the calculation just by clicking on this button, run calculation. You can see the process of the calculation. So I will again jump here because I've run the simulation before the webinar started. So now we can see that now that point 2 is simulated. You have the information about the time left, of whole computation, because I have set, I guess, 12 points to be simulated. Anytime you can, for example, skip to next point, and what is important, anytime you can generate the report. There are two buttons, which is also new features. You can generate the light report, which will show you the actual data of the simulation and is generated very quickly. So when I'm clicking on it, so now the light report is generated, and when it is generated, it will appear automatically in this right window. And when the mesh or when the computation is finished, then we can click on full report to see the full report. So for example, here we have the light report, which shows basic information and important convergence of flow rate, residuals, and, for example, fun characteristic and efficiency. Because we have only 1 point, but we can see that first point has 81% in efficiency. And at the end of the computation, we can, which I have here, we can see all is done, and I can generate the full report, which takes more time. And now I would like to briefly go through this report. You can see basic information about the simulation, for example, Y+, about the mesh, wall clock time, so the time, overall time of the simulation, fun characteristic, which is the graph showing the numbers psi versus phi, which is the special variables for funds. Efficiency, of course, because I have defined the old one. So the green one is my previous simulation with some different parameters or different geometry, and the violet one is the actual graph of the efficiencies. So this is a really nice feature because you can directly compare different simulations. And the report contains other variables, for example, torque, total pressure difference. Always you can see the graphs and the numbers in table for each point, and so on and so on. There are a lot of variables, for example, total temperature. The next one is velocity magnitude per interfaces, and so on. And what I would like to show you is the blade-to-blade view, which I have defined. So, for example, setup 1 was the static pressure at the height 0.25, and for each point you can nicely see the static pressure distribution in the blade-to-blade view. And for example, here we have plotted relative velocity with LIC filter, which is the streamlined filter. And again, you can nicely see, for example, I guess 0.4 has the best efficiency, and you can see that the points with lower efficiency has more recirculation between the blades and so on. So you can nicely analyze the results. And the last one was meridional average. So nicely, so you can see meridional average. For example, here we can see the total pressure. So this was the automatical evaluation, but you can also do your own visualization. For example, I prepared here. You can visualize just any part of the geometry with, for example, this total pressure distribution. You can visualize whole geometry, for example, with static pressure distribution. You can visualize Y plus if you are really interested in turbulence model, so you can nicely see in which part you have Y plus in the correct range and so on, and a lot of other filters you can apply on your geometry. Okay, so I think my time is almost up, so I will just summarize. So as you have seen, the TCFD is a great, easy to use and powerful tool for detailed evaluation and validation of your geometries. So basically in CFturbo you can design your machine, and then by a few clicks, even without any deep knowledge of CFD, you are able to validate your geometry. And on the other hand, the TCFD can be scripted and therefore very easily incorporated into your current CFD workflow, for example. So using CFD turbo machinery evaluation has never been easier. So my time is up. So I have to hand back the presentation to Luboš.
No, it's okay. Just take your time.
Yeah. No, really, I'm finished. Thank you.
Okay. So
you will. Okay, nice.
Okay, thanks. Thank you, Radek.
You're welcome.
So is it back on me? I guess it is. Okay. So yeah. So thank you, Radek, for your live demo. And yeah, so I think it's time to go ahead. So let's move in our webinar. And yeah, now it's time for your questions and our answers. So please feel free to put your questions. We are going to answer them right now. So yeah. So yeah. Some questions are already answered in writing, but still I would vote for answering them in just answer them. So yeah, so I will read the question and ask the answer. So the question number 1, is it possible to have a constant diameter for the housing with impeller in the middle, not like a spiral volute from Philip question? Oliver, would you just comment?
Yes. As far as I understand this question, one would certainly not use to this end a volute to design this component, but a stator. And with a stator, you can have again a lot of different shapes. One would be, for instance, a shape with a constant outer diameter. So I hope that answers the question.
Okay, maybe, yeah, let's do it that way. Answers on Oliver and CFturbo will be answered by Oliver, of course, and perhaps I will make you a presenter, because there's a chance you would need to show something. So yeah, it's,
okay.
Yeah, we can see CFturbo now, and so I will read another question. So, question to Oliver: how to address the air with dust particle at elevated temperature? Flue gas delivery. Yeah, it's this.
In the design process,
Oliver, we can't hear you now, I have to say, right? So, at least me, I can't hear you. Okay, so it seems we have lost the connection with Oliver. So I will continue with other questions that are addressed to machinery CFD, and then let's see what we can do with that. So okay, so these two questions are answered. Yeah, the next question on turbo machinery CFD is, yeah, is it possible to simulate tube phase flow, e.g. liquid-liquid in TCFD through pumps from Philip? Yes, yes and no. In the graphical interface, it's not available yet, this option. But what's important to note is turbo machinery CFD is based on OpenFOAM, and with every delivery of turbo machinery CFD, also the full version of OpenFOAM is delivered. So basically, this is also the answer for all the other questions of this kind. What is possible in OpenFOAM is also possible in turbo machinery CFD, because the turbo machinery CFD is bigger package than just an OpenFOAM. So yes. For your information, in OpenFOAM there is a huge family of volume of fluid, family of solvers, and yes, also pumps can be simulated with this interFOAM family of solvers, but it's not yet implemented in the graphical interface of turbo machinery CFD. So but we can discuss this in detail. You can contact us regarding this. Okay. Yeah, the next question. Is it possible to import and merge other external STL geometries for ducts, filters, etc., and solve it in turbo machinery CFD from Alistair? Yes, it is. Absolutely. Yes, absolutely. You can import the complete mesh, or you can import just any number of STLs. You can merge them. You can play with them. You can connect them and reconnect them. So it's really the options are really wide. Yeah. So, well, question on, yeah. How about adding and solving with a heat source? For example, a motor, which could be, yeah, in the fluid stream for axial setup. Question from Alistair. Yeah, and this is the same answer as the last answer. It's not yet in the graphical interface, but in general, it's possible, and it's not a big deal or a very big deal, because it's in OpenFOAM there is at least heat sources and conduction of solid parts. It's possible. So, and also wide range of boundary conditions of heat sources. So the answer is yes, but not directly from the graphical interface. Yeah. The next question: do all the setup need to be done in ParaView? I answer this. No, but it depends how. It depends on the meaning of your question. But no, you do not need to set up everything in ParaView because the machine CFD has many default parameters that are set automatically. So there is only a few parameters you have to set, like number of processors you want to run and perhaps number of points and speed lines. This is what you should say. And yeah, so and if the question is meaning whether it's ParaView or text file, so yes, you can, of course, you can set everything in the text file and run it and and open it in ParaView in the .tcfd format. Okay, there are some other questions. By the way, Oliver, can you hear us? And
yes, I'm back.
Okay, perfect. Okay, so okay, yeah. So very well. So everything works. So let's get back to the question. I think you were answering the question from
yes,
Ebasis. So it was the first one, and there is also second question. What is the specific application for semiconductor industry?
The specific application is just the cooling of chips, processors, and stuff like that. Because in almost any computer, there are fans implemented to serve for cooling purposes. So that's the main application.
Okay, and I think there's still a few questions on you, so I will switch back to you the presentation and the next question is whether the slip factor is decided by the software itself, or it may be you need to calculate it your own.
No, you don't need to calculate it on your own. There are these modules implemented, and once they have been chosen, they will be considered and in the design process. And everything, especially the calculation of the slip or the deviation angle, is then done by CFturbo, for instance. So if I, for instance, switch to the Gülich-Wiesner model and I switch calculate, then the deviation angle is calculated with 28 degrees according to impeller diameter, design point, and of course the slip model given here. So everything is always proposed by CFturbo, but of course one can override it and can adjust things in accordance to its own needs.
Okay, thanks. The next question on CFturbo is, would you expect this impeller design to meet the required duty point upon the first attempt?
If it was like that and we wouldn't need TCFD, well, it depends very much on the design point and the machine you want to design. Sometimes it's quite close, so we have customers that don't use simulation techniques at all, but most of the customers need a couple of loops or iterations before they get to the best or to the design they want to reach. But because everything is parameterized, and also the interfaces are there, it can be done quite quickly in a decent time scale.
Okay. The next question on CFturbo is it possible to use or transport the geometrical parameters of the CFturbo model for the parameter optimization in other programs?
Yes, it is. If I go back to our export panel, one can see that there are a lot of interfaces implemented. So we have, for instance, general geometry formats, which are text or XML data. Then we have neutral 3D geometric formats, step IGES, STL, BREP. We even could export well, not very high quality tetrahedral volume mesh if we want. Then we have these interfaces to the CAD packages, and of course a big deal of CFD packages that might be used at the customer side. And everything can be also scripted and can be used in a batch run, which means one could also incorporate CFturbo in an automatic optimization workflow.
Okay, yeah. Optimization is very popular, and it's a huge trend in CAE last years. So yeah, very useful. Okay, the next question. Does CFturbo predict the required power from Harry?
It does. We have implemented a performance prediction. I just want to get rid of some additional curves, and underneath, beneath the values we have here is also what we call the required power, and that can be estimated here. But of course, the accuracy of that implemented models is very poor if you compare it to CFD simulations, and that's why we always have this warning here, because it just depends on a couple of geometric parameters, a couple of empirical coefficients, and that's why I would always recommend to go into CFD and validate the power and the performance of the machine there, rather than using that simple performance prediction here.
Okay, thanks. The next question, how many types of volute does the software support? Do not mean the sectional shape, but their classification, such as internal, external, or center type, e.g. the internal one is famous for its extreme compact size, but prone to lose its total pressure along with the volute from Bhargav. So would you, Oliver?
Right. Yes, they are all the available shapes are given here, and it's not only the shape that can be chosen here, but also the kind of whether it's external or internal. So, for instance, what we call the round internal one would be the one that was probably asked for, and that would yield a very compact design, but with the disadvantages that were mentioned in the questions. So they are given here, and they can be found here. And yeah, probably the most important thing is that what we call round internal, where you get a very small outer diameter.
Okay, and perhaps the last question on CFturbo is, I notice you changed the meridional contour in CFturbo from the default. Is this to improve the efficiency of the impeller or meet space requirement? Are you looking for a constant velocity across the contour?
Well, I didn't do that for a certain purpose. I wanted to have it, I wanted to fulfill the space requirements, and always if I look at the velocity field, I want to avoid high or areas with high accelerations. So that are the two reasons for changing the shape of the contour in that webinar here.
Okay. Yeah, and I think this is it, at least for now, and I will switch to Radek. So are you ready? So there's a question. How about using LES or DES turbulence model in TCFD from Jan?
Yes, it can be, not implicitly, because we at this point, at this version, we provide just K omega SST and K epsilon and laminar turbulence model, but also we provide transient simulations at all, and using actually the video you could see before the webinar started was generated using TCFD and using DES turbulence model. And I created a simple script which can change the turbulence model and change it for DES modeling. So it is not available implicitly, but it can be simply modified using the scripting menu. So basically, it is available, and we can provide a script by no doubt. Yeah. So it is it can be simulated in TCFD, and both LES or DES. Basically, in general, any turbulence model which is available in OpenFOAM.
Well, thank you, Radek, for this. And perhaps the last questions from today's webinar is from Harry. So sorry, last question: how close is the performance prediction on CFturbo for this particular example to the CFD software? Well, it's really, yeah. I have to say I'm not the right person. Perhaps Oliver, would you try to say to answer this or comment?
Well, we can just quickly compare our data. So our performance prediction, well, in that case, it is somehow tuned to meet the global setup. So it's the total pressure difference in the design flow value is very close to this design point. So it's 265 bar. And Radek, could you?
It's somewhere here. 26. Well,
let me.
Here.
Well, let me tell you the flow value in cubic meters per seconds. Well,
okay,
quickly.
The best efficiency point in the simulation, which is this one, which is a 1/4 point, has 11.58 kilograms per second. But yeah, this is in kilogram per second and not in cubic meters. So times 0.2 or something like that, maybe.
Okay, but the global setup flow in kilogram per second is something like 10.5 or so.
Okay. Yes. It's quite
very good. And what is the pressure difference there?
And pressure difference for this point is total pressure difference 27,000 circa.
Okay, so and our prediction gives 26,500 or so.
Yeah.
At least let's say it's comparable. Yeah,
yes.
Well comparable.
Yes.
Okay. So I think this is it from us from today's webinar. So it's time to finish. So I will only finish with my presentation. Yeah. So it's So it's time to finish. So feel free to contact us. I'm sure you know very well how to do that. The questions about CFturbo are to be sent to CFturbo company. The questions about Turbo Machine CFD are to be sent to CFD support company. We will gladly support you in your Turbo Machine projects. It's our job and also a pleasure for us. So anything more to say, Oliver?
The only thing I want to say is thank you for your time, and thank you audience for your time. And as Lubaš said, if there are any questions, please don't hesitate and contact us. Thank you and bye-bye.
Okay, thanks. And Radek?
Well, just thank you for your attention and have a wonderful day.
All right, so so thank you for your attention. We are looking forward to collaborating with you, so stay tuned and see you someday somewhere. So bye-bye for now. Bye-bye.